So some of you weren't here on Friday. I mentioned to the other classes that in a perfect world, I would have time to reteach some of the material, but I don't really. Um, we finished 6-4 last time. The only thing I didn't go through is the last paragraph on page 326, but I think it's pretty straightforward if you read it. The things that we covered on Friday were complicating factors associated with root structure. So for example, if you're short electrons, and you know that the atoms in the molecule have to obey the octet rule, that means multiple bonds. For every multiple bond you build in, you get 2 electrons closer to having what you need. If you're in a scenario where you have too many electrons, that means you've got a central atom that has an expanded octet that has to be a 3rd period element or higher. And that one's easier than multiple bonds because you just satisfy all the octets, and any extra electrons you have, you just pair up and put in the central atom. We also did something called resonance, which is explained in the book, but the diagrams in the book are insufficient. And I mentioned in class that if I ask on a test, and test now is final exam, if I ask you to draw resonance structures, I will say, including the electrons involved in resonance. And because it isn't in the book, that last part, I'm going to go through a couple of the review questions, and I'll pick one where the resonance thing is required the way I did it on the board on Friday. Taking an audio recording of the class is better than nothing, but it doesn't help you with something like that. So let's just touch on a few of the questions at the end of 6-4 real quick, and then we're going to move pretty rapidly into 6-5. So if you look at number 3 on the bottom of page 329, that question is intended to help you get to the what's the most likely skeleton. So if you look at A, phosphorus and chlorine, which is the most likely element that's the central atom? Which of those two? Phosphorus or chlorine? It's phosphorus, which makes sense. It needs 3 electrons to be like the nearest little gas. Chlorine only needs 1. That's also the atom with the lowest group number. It's also the atom of that pairing with the lower electronegativity. That usually suggests the central atom. If you look at the next one, the same reasoning will get you to nitrogen. Nitrogen needs 3, oxygen needs 2. Nitrogen has a lower group number. Nitrogen has a lower electronegativity. Carbon and sulfur. Now, carbon and sulfur have the same electronegativity, but carbon needs 4 electrons, sulfur only needs 2. So it makes sense that carbon will be the central atom. And notice that sulfur is right underneath oxygen in the table. So if carbon forms a compound with oxygen, CO2, it's not out of the question that it might form a compound with sulfur, CF2. Nitrogen and hydrogen, that's easy because hydrogen can never be a central atom and have any more than one bond. Oxygen and fluorine. Oxygen needs 2, fluorine needs 1. Now, in the vast majority of molecules with oxygen in them, oxygen is written last. That's because oxygen, the element you write last, is the element with the higher electronegativity. The only exception to that is when oxygen starts with fluorine. So, for example, if you were going to write the formula for a compound of chlorine and oxygen, Cl2O. But if it's fluorine, it's not going to be F2O, it's going to be OF2. Because fluorine has an electronegativity of 4, oxygen has an electronegativity of 3.5. If you look at number 5, the Lewis structure, actually, while we're here, look at number 4. Which of those 3 skeletons is the most likely, based on your knowledge of skeletal building? Well, maybe a better way of saying it is which ones have to be wrong? Ask yourself one question. How many bonds can fluorine have? One. That means the only possible skeleton. Now, all the electrons aren't in there, but the only possible skeleton could be the one in the top right. Notice that each carbon has 4 bonds. Each fluorine has 1 bond. If you look at number 5, all of those, and it continues on the next page, there are no complicating factors there. There's no expanded octets. There's no multiple bonds. There's no incomplete octets. If you look at number 7, each of those central atoms in the skeletons have an expanded octet. So sulfur, phosphorus, iodine, selenium, they're all elements 3rd period or bigger, which means we have access to the d orbitals. But if you are going to have an expanded octet, it has to be a central atom. Number 8 is an example where notice that the last 2 say in brackets resonance structures. So partly for practice, partly to benefit the people that weren't here on Friday, I want to do nitrate. Now, how would that be worded on a test? Well, probably the nitrate anion can be represented by 3 resonance structures. Draw the structures, including the electrons involved in the resonance. And you're going to see when we do it that it's remarkably similar to the carbonate of it. The only difference is that instead of a 2- charge, we've got a 1- charge. So there's the formula. Now, if you forget to add that extra electron, consistent with the negative charge, you get an odd number of electrons. Nitrogen has 5. Each oxygen has 6. So 3 times 6 is 18, and 5 is 23. And if you got 23, obviously the signal is you did something wrong. You thought it had that negative charge. So 5 plus 3 times 6 is 1. So 24 days. If it's an ion, the protocol is to wrap it in square brackets and to with the charge outside. Nitrogen is going to be a central atom. It needs 3 electrons. Oxygen only needs 2. It's got the lower electronegativity. This is of the form A plus N. So it doesn't have to be like an equilateral triangle. You could have 1 oxygen here, 2 here, or 2 here and there, or 2 here, 1 here. It doesn't matter. I just have a tendency to draw it from the center. So let's say that's our skeleton, right? And we got a rapid and spin. All we're doing is following the steps. To construct the skeleton, which is reasonable, and oxygen doesn't like to stick to itself, so we use sticks. So we got 18 left. How many do we need? Well, each oxygen needs 6, that's already 18. And the nitrogen needs 2. Right now, nitrogen's associated with 2 through 6, so it needs 2 more. Each oxygen is associated with 2, so they need 6 more. So 18 left, but 20 needed. Nothing in here can have an expanded octet. Nothing in here can have an incomplete octet. The only ones having incomplete octets are possibly beryllium, boron, and aluminum. Nitrogen isn't one of them. So as we learned last class, if ever you're short electrons, you would modify the skeleton by adding a multiple bond. And every multiple bond you add gets you too closer to having what you need compared to what you have. So let's, for argument's sake, let's put the double bond. So we've got 4 bonds now. So we have 6, 8, which means we got 16 left. But if we've done it right, we should need 16. Each oxygen still needs 6, so that's 12. Nitrogen doesn't need any. But this oxygen needs 4, because it's already associated with 4. So 6 and 6 and 12 and 4 is 16. 16 left, 16 needed. So we think, all right, let's just put the 16 where we need, where they're needed again, just following steps. and then see if it works. Well, we always satisfy peripheral atoms first. There's 6. There's 12. And let's put the 4 that are equal there. Okay. And let's make sure all 24 are accounted for. 2, 4, 6, 8, 3, 4, 4, 5, 16, 18, 20, 24. So everything has an offset associated with it. All the electrons are arranged in pairs. It matches the formula, so it's probably 7. Recall that we talked about bond strength and bond length based on multiplicity. Double bonds are shorter than single bonds, and they're stronger. And we have some pretty accurate tools at our disposal to measure bond length and bond strength. So if this is the correct structure, then 2 of the bonds should be longer. 1 of the 3 bonds should be shorter. 1 of the 3 bonds should be stronger than the other 2. In other words, we should have 2 single and 1 double. When we look at the nitrate anion, just like the carbonate anion, we see there are no double bonds and there are no single bonds. Every bond is a little longer than a double, but a little shorter than a single. Every bond is a little stronger than a single, but not quite as strong as a double. It's as if that pair of bonding electrons was thrown into the structure and kind of averaged between each of the pairs of atoms, smeared out, if you will, equally between each of those 3 bonds. Chemists use the term delocalized electrons. Lines and dots can't show it. So here's one of the limitations of Lewis structure. If we remember what electrons really are, that's not surprising. They're charged particle waves. So to have them kind of delocalized or smeared out is not really that weird if you remember how weird they are anyway. But the point is, Lewis structures can't show that. Lewis structures can only show stationary electrons, not delocalized. They only show localized electrons, lines and dots. So as an admission that Lewis structures have their limits, we use the term resonance, which suggests that that double bond somehow resonates between each of the 3 pairs of atoms, which it doesn't. So when a question said the resonance structure, the nitrate anion can be represented by 3 resonance structures. None of those things exist. It's just the best we can do using Lewis structures. So, and that's resonance is often the case where we've got multiple bonds and single bonds in the same molecule on either side of a central atom. So, in the book where we have carbonate C here and 2 minus out here, the 3 diagrams just have this effectively turned. So if we call this, you don't have to write this down, but let's say that's at oxygen A, oxygen B, and oxygen C. If all I do is turn this, I haven't moved the double bond. It's still between nitrogen and oxygen A. And that's why the diagrams in the book aren't sufficient. You could argue, well, we just took the diagram and did this, and then did that. To show the bond actually moving, you need to be a little more inclusive in the diagram. So we got 3 possible positions for the double bond, so we got 3 resonance structures. So let's imagine we want to move the double bond here. Okay, that's easy. Let's just do this. Not that easy, because that gives this oxygen 10, which you can't ever have, and it gives this oxygen 6, which you can't ever have. So rather than doing that, it's a 2-step event. Let's imagine, pick any of those lone pairs. Let's imagine that this lone pair all of a sudden became bonding. I've heard teachers represent it as that pair of electrons flips in. Don't draw a solid line in. That means the bond's already there. If that bond forms, this bond has to unform. If you will, that pair of bonding electrons has to flip out. And that gives rise to resonance structures. Here's our central nitrogen. This oxygen now is no longer part of the double bond. It's got the 3 pairs of electrons. This oxygen we didn't do anything to. Well, this oxygen is now involved in a double bond. And make sure when you add the electrons, you don't put those there. So here's the double bond that's had its position moved. Okay. Now, what if we want to move it here? Well, every position we want to move the double bond to, a lone pair on the oxygen, where we want that double bond to be, has to become bonded. So doesn't matter which pair we pick. Let's imagine that this pair of electrons becomes bonded. And then the dash line there. If that becomes bonding, if that becomes bonding, this must become non-bonding. And that gives rise to resonance structure. You didn't do anything to that oxygen, so it's still got 3 pairs of electrons. This oxygen, we regenerated the 3 lone pairs. This oxygen now has a bonafide double bond. And those are gone. So that's where the electron with that oxygen. Notice that all of them have all the atoms obeying the octet rule. All the electrons are in pairs. Correct formula. We don't have to show this one turning back into this. But when I say including the electrons involved in the resonance, this is what I mean. You have to have a pair flipping in and a pair flipping out, yielding the next one. And depending on what you decide to flip in and flip out, that has to sort of bear out in the next item. You can't show that and then over here show a double bond here. The other thing you got to remember is when that goes away and becomes this, you have to leave a bond space there. So count electrons 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But if you forget and then do this, that's too many electrons. And you can't have an expanded octet. A number of you on your quantum mechanics test had the wrong number of errors. And it's because you don't count electrons. And that's particularly important with ions. Add electrons for anions. You add as many electrons as the magnitude of the negative charge. You remove as many electrons as the magnitude of the positive charge. For those of you that weren't here Friday, except for this, the rest of the stuff we did is in the book. So read the book. I sometimes get the impression that you don't read the book. You listen to what I say and maybe take notes, but you don't read the book. And the book is intended to be read. That's why we wrote it. And we wrote it in such a way, for the most part, that it's pretty user-friendly. If you look at the last question there, number 8, that was the last paragraph that I didn't teach on Friday. And that's related to the fact that we don't usually employ Lewis structures for big, complicated molecules. For example, you would never see a Lewis structure for a molecule of glucose, C6H12O6. We have ways of representing those diagrams, but Lewis structures aren't usually what we use. If you're given a formula for a compound that potentially could have more than one central atom, probably I would give you the skeleton. And that's what I've done in number 9. So The skeleton is the first thing you do after you determine number of valence electrons. So if you look at the first example there, what is that formula? C2H2. So you could calculate the number of valence electrons. I've given you the skeleton, that's all. And the idea is you take it from there. You can count valence electrons. What do you have? What do you need? For that one, you're going to end up being 4 electrons short. So you need a triple bond between each of those two carbons. The second one, it said oxygen doesn't like to stick to itself, which is true, except if it's peroxide. That's hydrogen peroxide. But the electrons aren't all there. So how many has been used to construct that skeleton? And then you have, and then you got left, put them where they're needed. The next one, C2H4, you're also going to be short electrons, but you're only going to be short 2, which means the bonds between the carbon have to be double. You can't have double bonds with hydrogen. That compound, when you finish it, is called ethene. That's one of the things that's released from apples as they ripen. And I think I said this before, if you want bananas to ripen, if you get a bunch of, you need bananas, you go to the store and all they have are green bananas. Put them around apples in a bowl. The apples will release ethane gas, and that helps the bananas ripen faster. The one on the bottom, there's no multiple bonds there. That's molecule of methanol or methyl alcohol, the simplest alcohol, which hopefully we'll get to when we arrive at organic chem. Okay? Lewis structures aren't difficult unless you don't practice them. Yes. So let's move right into 6.5. Lewis structures in and of themselves, I mean, are they useful for some things? Yeah, they're useful basically for connectivity of atoms. But that's not really their main purpose. Their main purpose is, if they're drawn correctly, to use the symbols of dots and lines and elemental symbols to guess the 3-dimensional shape of whatever we've drawn. And that's the title of section 6.5, the shape and behavior of molecules. And the first part of 6.5 is the shape part. So we're going to use Lewis structures to predict 3-dimensional shape. And the second part is the behavior. In other words, here's a formula. Can you draw a Lewis structure? From that Lewis structure, can you predict the shape? Draw it and name it. From that shape, can you then infer something about behavior? So let's look at the warm-up and top of page 338. Remember, here is easy. Electronegativity type, we know what that is. Use your answer to question 1 to define the term polar covalent bond. You know, covalent means sharing, polar means unequal sharing. So it's a molecule or ion where the bond have sufficiently unequal electron sharing that one end of that bond is a little more negative. And the more electronegative atom towards itself, the other one is a little bit positive. That has electrons removed. If a substance contains polar molecules, notice molecules in brackets there, how might that affect its melting and boiling point? Right? This is part of the behavior. If I have a molecule where the bonds are polar, it doesn't always mean the molecule working. But let's say I have a molecule with polar bonds, and the shape of the molecule is such that one end of that whole molecule is a little bit negative, and the other end's a little bit positive. That means that polar molecule is likely going to want to stick to other molecules like it. So the negative end of one molecule is going to want to attract the positive end of another. And the best example of that is this. Right. Water shouldn't stick to itself as well as it does based on its molar mass. For example, carbon dioxide. Carbon dioxide has a central atom and two peripheral atoms. It's way heavier than water, more than twice as heavy. Yet it's a gas. Water, on the other hand, only has a molar mass of 18 grams per mole. It does have a central atom and two peripheral atoms, but based on its shape, it sticks together really well. Drawing Lewis structure serves an important purpose beyond indicating connectivity of atoms and molecules and polyatomic ions. The two-dimensional collections of symbols, lines, and dots often allow us to deduce the three-dimensional shapes of the chemical species they represent, without the need for complicated bonding theory. Determining the shapes of those species is an essential part of understanding and predicting their physical and chemical behavior, ergo the title of the section. The process of inferring a three-dimensional shape from a two-dimensional Lewis structure is based on a very simple premise. Valence electrons represent regions of negative charge that repel each other. Any group of valence electrons associated with the central atom. So there's a clue. We're trying to do the shape. Look at what's on and around the central atom. Will tend to orient themselves in three-dimensional space around that so as to minimize the repulsion between them. Now, how do they do that? Well, they're going to try to get out of each other's way, as far away from each other as possible, while still remaining connected to the central atom. Examples of such groups of valence electrons include a lone pair, a bonding pair, or multiple pairs involved in a double or triple bond. And again, that would be on the central atom. In short, while remaining attached to the central atom, these groups of electrons will position themselves as far away from each other as possible. This is the fundamental principle behind the valence shell electron pairing function. Valence shell electron pairs with each other. And that dictates all the shape we're going to talk about. One of the early practice problems I asked you to do explore was carbon tetrachloride. There's nothing complicated about this. Everything we like to do, the electrons we needed, match the electrons we had. Now, remember I said don't try to make Lewis structures in 3D. But let's say carbon tetrachloride, let's say that did represent its actual shape. If it was a flat molecule, what should those bond angles be? This was a two-dimensional molecule, yep?
90 degrees.
90, should be 90. Each of these pairs of electrons represent regions of negative charge, clouds that repel each other. If that was the correct structure, then those clouds of repelling electrons would form a flat shape, right? But 90 degrees, let's imagine the carbon in the center. Here's the valence, the pair of valence electrons attached to the carbon, the sharing right here. If that's the way it really was, then you would expect those bond angles to be 90. But this thing does not want to stay like this. That's what it wants to do. And that's better than 90. That's called a tetrahedron. And those bond angles are 109.5. Does that mean if we blow up balloons and tape them together in their center, they approximate the shapes that these molecules and polyatomic ions are going to adopt? Yeah, it does. Notice how I cleverly chose a balloon. So, central atom is here. Two pairs of two valence electron pairs on either side of the central atom, because it has to be linear. That's the shape they adopt. We don't have to tell them that, just take two balloons together. They have to be linear. 3 pairs, assuming they're all the same size, it'll be a flat triangle. 4 pairs is this. We call that a tetrahedron. 5 pairs, there's a goofy name for that. We're going to learn about it's called a trigonal bipyramid. Bipyramid just means 2 pyramids stuck together. And this one is 6 balloons. We call that octahedral. And you might think octa means 8. This one's 6 balloons. Well, hedron means side. So you can imagine a 4-sided pyramid up here, and then a 4-sided pyramid down here, octahedron. You know, aren't going to have to blow up balloons to do a test on this stuff. You're just going to have to remember. But it's almost that simple. Okay. Now it gets complicated when some of the electrons aren't bonding pairs, when some of them are lone pairs, and we'll see that as we move through. If the electron groups are bonding electrons, in other words, if there's atoms out here, let's say that's the central atom and there's an atom out there. So those are bonding groups. Then the peripheral atoms they bind to the central atom adopt the same arrangement as the electron groups would do. So in other words, I got an atom there. Let's say I've got an atom there, there, and there. That's going to be a flat triangle. As my balloons demonstrated, if I got an atom there, and there, and there, and there, that's going to be a tetrahedron. Okay. Several experimental tools that allow us to determine molecular geometry. So we can find the nuclei. We can easily find where the nuclei are. And when we do that, we find that the shapes, yeah, they look like that. In the solid phase, we can use X-ray crystallography as well as neutron and electron diffraction. You don't need to know how that's done, just know that it can be done. And in the gaseous phase, that's for the gaseous molecules, gas electron diffraction usually is. And all it does is bear out what Vespers theory suggests should be the case. And if it didn't, then we'd be wasting our time. Electron groups and their repulsive effects ultimately determine where and how the nuclei of the atoms in a molecule or polyatomic ions arrange themselves in 3-dimensional space around a central atom. And it's the shapes of those things we really care about. So we're in the shape part of shape and behavior. We'll consider each of the 5 electron group arrangements. 2 groups, 3 groups, 4 groups, 5 groups, 6 groups. And you say, well, what about, why not just 1 group? Well, 1 group means you don't have central atom. We got an atom here and an atom here. That's got to be linear. So we don't need Vespers theory for that. Let's begin that by assuming that each electron group we're talking about is a bonding group connecting the central atom to peripheral atoms. And a bonding group could be 1 pair of bonding electrons, a single bond. It could be 2 pairs of electrons, a double bond, or it could be 3 pairs of electrons, a triple bond. It doesn't matter. They end up being the same shape, okay? We'll then expand our discussion to include lone pair electron groups on the central atom. So first, we're just going to consider bonding groups, where they've got atoms on either side of adjacent nuclei, and then we'll incorporate lone pairs in the central atom. We'll expand our discussion to include lone pairs. As a general notation, the central atom we're going to call A. The peripheral atoms we're going to call X. And the number of lone pairs on the central atom we're going to designate as E. And sometimes this is called AXMEN notation. That's the number of atoms bonding to the central atom. That's the number of lone pairs on the central atom. So the subscripts are the same we use for chemical formula. And notice that E doesn't tell us the number of non-bonding electrons in a circle. It tells us the number of non-bonding pairs. So E1 would mean one pair of electrons. And E2 would mean two pairs of electrons on the central atom. And we're going to start simple and get more complicated. So the simplest one is AX2, two bonding groups. When two groups of bonding electrons connect the central atom to two peripheral atoms, the notation AX2 applies. And because I'm too lazy to blow up balloons, start taping them together, let's look at an AX2 arrangement. Let's let that be our central atom. And let this be our peripheral atom. So that's AX2. Hey, well, what about AX? Well, pretty much linear, right? So we need at least two groups of electrons. The surrounding atoms are as far as possible from each other on opposite sides of the central atom, which means this XAX bond angle has to be 180. That's the farthest away they can get from each other. And notice in the diagram here, all of these are AX2. But the bonding in all of them is different. So beryllium dichloride could be this. Beryllium doesn't have an octet, but it can't anyway. It's only got two valence electrons. Notice both single bonds. Notice in this diagram, we also got three lone pairs in each of the peripheral chlorines. It's still AX2. Carbon dioxide is also AX2. The bonds aren't single, they're double. And instead of three lone pairs on each peripheral atom, there's only two. It doesn't change anything. It's still AX2. Down here, I got a triple bond and a single bond. No lone pairs here, only one lone pair here, but it's still AX2. So the bond multiplicity doesn't matter. All that matters is how many X's, which are bonded atoms, around the central atom. Okay? Always linear. Bond angle 180 degrees. Now, as long as we're here, look at that straight molecule. What's the electronegativity of beryllium? You look it up on your table. Beryllium's 1.5, okay. What's chlorine? 3.0. That's a pretty polar bond, isn't it? It's 0.2 away from being ionic. But look at the shape. That bond is really polar. So violent. And because that bond's moving 180 degrees, it's like an equal tug of war. The bonds are polar, but the molecule isn't, because the bond dipoles cancel. Okay? Same with carbon dioxide. Carbon's 2.5, oxygen is 3.0. That's also 1.5. And there's not just one pair of electrons shared equally, there's two. But once again, because the molecule is linear, it's non-polar. The molecule isn't polar. So carbon dioxide doesn't stick to itself, which means when I breathe out, carbon dioxide, a gas. This one, though, this one should be full. Carbon's 2.5. Nitrogen is 3.0. And we've got three pairs. So not only is that bond polar in the direction of nitrogen, but carbon is also pulling electrons away from hydrogen. So this molecule is polar. The bond dipoles reinforce each other. There's bond dipoles in all of these. 3.5, 2.5, 3.0, 1.5. But in here, the bond dipoles cancel based on the shape and symmetry of the molecule. Here they go. And that's going to be the behavior part of this section. Okay? But all of them are shaped the same, as long as they're AX2. As you might expect, as we start adding electron groups to the central atom, we probably add a little bit of complexity too. When three groups of electrons orient around a central atom, two shapes are possible. And the two shapes are based on the fact that we can have a lone pair on the central atom. If all of those bonding groups are stuck to atoms, if it's AX3, and let's say for argument's sake that all the X's are the same. They're all the same size. Now, whereas in a linear structure, it's 180, what do these bond angles have to be? They're going to add to what? 360? You guys ever had geometry in any of your life? What's 360 divided by 3? Feel free to break out your calculator if you need to. So these bond angles have to be 120, right? Okay. What do we name that structure? Triangular planar. It's a flat triangle. And once again, look at the symmetry. If these bonds are polar and all of these atoms are the same, the bond dipoles cancel. Now, we also have the option of taking one of these and replacing it with a lone pair. So this is AX3. And if you look down here, there's an example. Boron trifluoride. Are those bonds polar? Hell yeah, they're polar. But it's a flat, symmetric molecule. Molecule doesn't have one end more negative than the other, even with the bonds do. Now notice how this is drawn. Look at some of these symbols. They look a little goofy. Each of these lines are different. This line is just solid. That means it's in the plane of the board. So that means this line is dashed. That means it's going into it. I hold it like this. So this one is this. This one is that. And the one that's coming out of the rear is drawn by exaggerating. It's drawn like that. So it gets flatter as it moves away from the center. Stay away from it. So that is how that's drawn. Now, why am I going through that? Because when you have to draw the structure, you're going to have to know how to represent what's coming out and going in and in the plane of the board. Now, of course, you could also have drawn it like this, with all the lines solid. That would still be correct. But this is drawn intentionally on its side to give you an introduction to that terminology. And when we get to organic chem, that's going to be even more clear. Okay. Now, what if one of these things, let's say, I mean, fluorine's a pretty small atom. But let's say we replace one of the fluorines with something much bigger, like iodine. Let's say that's iodine. Now, this is a bigger atom. And if it's bigger, it's going to take up more room. And if it's going to take up more room, it's probably going to push these littler atoms closer together. So if this is much bigger, these bond angles here are probably going to be more than 120. And this bond angle is going to be less than 120. Does that make sense? If it does, then consider what happens if we put a lone pair on the central atom. Instead of being AX3, let's say it's AX2E. AX2E. Notice I picked a longer stick. It's because lone pairs take up more room. If we go up here, if one of the three electron groups is a lone pair rather than a bonding pair, we use the notation AX2E. It still adds to 3, 2 plus 1 is 3. But what we see doesn't include this because we can't see electrons with, for example, X-ray crystallography. We can find nuclei, but this is invisible. But what we see is this. So we call it angular or bent.
Hello, St. Thomas More. It is about time for us to head down to our house collective areas. So after I say this, you pack up your stuff. We are going to meet as houses in different common areas and then get called down to the gym from there. So Dublin, you are meeting in the Learning Commons. Canterbury, you're meeting in the CAP. London, you're meeting in the courtyard. Limerick, you are meeting in the multi-purpose room. Oxford, you're meeting in the gym. And Waterford, you're meeting outside the front foyer. All right?
What I'd
Go
like,
London.
what I'd like you guys to do for next class, read to the end of the shape part, which is up to page 336. Try the fraction problems on 337. As far as I know, Thursday's a full block. So I'm gonna do my best to get close to finishing 6.5. 6.5 is the end of the section, but we're not going past the bottom of page 345. Okay? When we finish 6.5, because we're not having a test on 6, I'm gonna pick an old test, the whole thing, and I'm gonna put it on the screen. Multiple choice and written response. So you'll see what kinds of things could show up when this is on the final result. And then we'll start organic chemistry. Okay?